Every quadratic draws the same shape, a single, smooth U-curve called a parabola. The whole topic is really one question asked over and over. Where does this curve meet the height of zero? Those crossing points are the solutions we are hunting for. But a curve can meet that line in three different ways. It can cross twice, just touch once, or sail clean over and miss entirely. Read on, and you will know in advance which of those three will happen before you ever draw a thing. The fastest route to the roots is factorizing. We rewrite the quadratic as two brackets multiplied together. Here, x squared minus 4x plus 3 splits neatly into x minus 1 times x minus 3. The numbers inside are chosen to multiply to 3 and add to minus 4. Now the trick: if two things multiply to give 0, then at least one of them must itself be 0. So either x minus 1 is 0 or x minus 3 is 0. That hands us the two roots directly, x equals 1 and x equals 3. Factorizing hides the most useful feature of all, the very bottom of the curve. Completing the square reveals it. We fold the same expression into a perfect square plus a leftover. X squared minus 4x plus 3 becomes x minus 2, all squared minus 1. That form is a gift. A square can never go below 0, so the smallest the curve can ever be is minus 1, and it happens exactly when x equals 2. So the lowest point of the parabola, its vertex, sits at 2, minus 1. The square form simply reads it off. Some quadratics refuse to factorize with whole numbers. For those, we complete the square on the general form a x squared plus bx plus c, and out drops a single master formula that solves every quadratic on Earth. No guessing required. Here it is: x equals minus b plus or minus the square root of b squared minus 4c, all divided by 2a. Feed in the three coefficients, and the plus or minus delivers both roots at once. It is the one equation worth memorizing for the whole of paper 1. Look hard at that formula, and one piece does all the deciding. B squared minus 4c, tucked under the square root. We call it the discriminant. Its sign alone tells us how many real roots exist, long before we finish the sum. If it is positive, the square root is real, and the plus or minus gives two distinct roots. The curve cuts the axis twice. If it is exactly 0, both roots collapse into 1, and the parabola just kisses the axis at its vertex. And if the discriminant is negative, the square root of a negative number has no real value, so there are no real roots at all. The curve floats entirely above the axis and never crosses it. Three coefficients, one quick subtraction, and the whole story is told. Quadratics also team up with straight lines. To find where a line meets a curve, we set them equal, which folds both into a single quadratic. Solving it gives the x values where they cross. Here a line slices our parabola at x equals 1 and x equals 4. Finally, a quadratic inequality asks not where the curve equals 0, but where it dips below or rises above. Find the roots first, then read the graph. The curve is below the axis only between its two roots. So the answer is a stretch of the number line, not just 2 points. Here is the whole unit as one poster. Every quadratic is one parabola, and solving it means finding where it meets 0. Factorizing splits it into brackets and reads the roots straight off. Completing the square folds it into x minus h squared plus k, which hands you the vertex, the lowest or highest point of the curve. When the numbers turn ugly, the quadratic formula solves anything, and the discriminant, the piece beneath its square root, counts the roots before you start. Positive gives 2, 0 gives 1, negative gives none. And the same shape meets lines and answers inequalities. And the boundary fence so you do not over-revise. Cubics and higher polynomials, the remainder and factor theorems, come later. The quadratic graph transformations belong with functions, and complex roots of negative discriminants are a pure 3 idea. Here it is the quadratic, solving it, shaping it, and counting its roots.